How are we doing today? This is Mr. Novak. Today we're going to be learning about Newton's three laws of motion, and we will be taking notes on this as we go. So it's important to make sure you're copying down the examples and taking really good notes. Okay, so let's take a look. Our first law of motion for Newton states that an object at rest will remain at rest, and an object in motion will remain in motion until acted on by an outside force or an unbalanced force. So let's take a look at two examples that we can use. Okay, so the first part, an object at rest will remain at rest. So let's take a look at a book. Okay, a book is sitting at rest on your desk, and it will remain at rest until an outside force or an unbalanced force acts on it. Okay, so what Newton's first law is really saying is that book is not moving and it wants to continue to not move. But something else has to come in and act on it in order for it to move, right? The book just can't move by itself. So there has to be an outside force or an unbalanced force that acts on it. So a push or pull, whatever you want to do for that book, that's one way, or that's the first part of Newton's first law of motion, right? For objects at rest. The second example deals with objects in motion. So if you're riding your bicycle, you will remain in motion until acted on by an outside force. Okay, so again, an object that's in motion wants to remain in motion. Okay, so the bike wants to remain in motion until it's acted on by an outside force. So one outside force would be friction. Friction is what would slow your bicycle down and would be that unbalanced force that affects its ability to stay in motion. All right, our second law of motion for Newton would be states that the net force on an object is equal to the power of its acceleration and its mass. So if we take a look here, there's this formula where we have force equals mass times acceleration. Okay, and that's just really the relationship that we'll kind of do some work with in terms of like the mathematical part of it. So as we're looking at this, really the kind of the simplified version of it, or kind of the easier way to digest, is saying that the force required to accelerate an object with a large mass is greater than the force required to accelerate an object with a smaller mass. Okay, so you're going to need more force. Okay, what that's basically saying is you're going to need more force when you're dealing with something that's larger than you are if you're dealing. You're going to need not as much force if you're dealing with something that's a smaller object. All right, something that has a smaller mass. So if we take a look at these two cars here, right? We have a bigger car, we have a smaller car here. Okay, so the larger car, right? It's going to take a greater force to accelerate because it has a larger mass, right? Now, if we look at this little car, okay, almost say like a toy car, right? It's only going to need has a smaller mass, therefore, it's going to have a smaller force that's needed to move it or to accelerate it. Okay, just right. It's based on size and the amount of how massive or how much mass it has, and the relationship. The more massive it is, the more force you're going to need to help accelerate it. Okay, and our third law of motion for Newton states that if one object exerts a force on another object, then the second object exerts a force of equal strength in the opposite direction on the first. Kind of like the best way to describe this is, and I'm sure you've heard this before, for every action there is an equal and opposite reaction. So let's take a look here. We have two examples. We have a hammer. So let's take a look at this hammer example. So if we have a hammer and we have a nail, okay? So a hammer exerts a force on a nail, and then the nail exerts a force that's equal and opposite back on the hammer, and it causes the hammer to suddenly stop. So if we have a hammer, right, it's pushing down, right? The force that it's using is a push, right? And it's pushing down onto the nail, right? So as the hammer is pushing down on that nail, the nail is also pushing back up, right, on the hammer with the force that is equal to the hammer. Okay, so it's going to keep going, right? Okay, as you hammer it in, right, it's going to keep going until it's in the wood, and then it's going to stop because it can't really go any further. But the force of the hammer is acting on the nail in a downward motion, and the force of the nail is acting on the hammer in an upward motion, or going up. Okay, and our last one that I think is a really good example is like a spaceship with a rocket, right? Okay, a rocket. Okay, so if we take a look at the picture here, the rocket has kind of the fuel or the exhaust that's coming out the fire that's coming out the bottom here, right? So that's pushing down, right? That's pushing down. And then we have our rocket, right? So the rocket, this pushes down, and the rocket itself is going to go up, right? It's going in the opposite direction. So as that fuel burns, right, that's our action, that pushes down, okay? And the reaction would be the rocket going up into the air, okay? So it's going in the opposite direction, right? It's an equal and opposite force for both of those, okay? So these are our notes. We have some other things that I want you to make sure we're finishing up. If you have any questions, be sure to ask me. Once again, this is Mr. Novak, and I'm signing off.